The structural survival of any submerged vessel depends entirely on the absolute integrity of its pressure boundary. A submarine is fundamentally a sealed steel tube designed to resist the crushing weight of the sea. Every opening cut into this primary hull introduces a catastrophic structural vulnerability. Yet British naval engineers built a massive class of submarine that broke a basic rule of pressure hull design. The K-class carried 4 boiler room air inlets, each about 37 inches in diameter. These were not minor valves or routine hatches. They were enormous openings leading straight into the boiler and machinery spaces. This extreme architectural compromise was driven by a single tactical demand. The Navy wanted a submarine that could, at least on the surface, keep pace with fast fleet units. Contemporary diesel technology could not reliably produce the horsepower needed to push a large hull through rough water at around 24 knots. In practice, steam turbines were the propulsion system designers chose to chase that surface speed. Installing a high-output steam plant inside a submersible hull created a profound engineering paradox. Steam propulsion requires 2 vital elements to function at capacity. It requires an immense volume of oxygen to feed the roaring oil-fired boilers, and it requires a massive exhaust system to vent the superheated combustion gases away from the hull. To accommodate this intense industrial process, the designers fitted the submarine with folding smokestacks and a series of 37-inch mushroom ventilators. When the submarine operated on the surface, these massive vents stood wide open, drawing in the sky to feed the fires below. The vessel functioned exactly like a surface warship, riding high and fast, driven forward by the immense power of its steam turbines. But a submarine must eventually dive, and the transition from a surface steaming configuration to a sealed submersible state was an intricately dangerous mechanical sequence. Before the steel hull could safely slip beneath the waves, the boiler fires had to be killed, and the steam system shut down and isolated. Most critically, every intake, exhaust, and ventilator opening had to be closed and physically secured. The smokestacks folded down into the superstructure, and heavy mushroom covers were driven onto their seats by mechanical gear and careful human checks. Those covers had to seal tight enough to restore an unbroken pressure boundary before the ocean took the deck. The entire survival of the submarine relied completely on this mechanical actuation. If a single heavy cap failed to lock perfectly into its seat, any one of those boiler room inlets would instantly become a massive floodway, funneling the full weight of the ocean directly into the deep boiler rooms. The vessel designated K13 was an immense submarine built to live with that compromise. She measured 339 feet in length, making her one of the largest and most complex submarines constructed at that time. Operating such a vast and intricate hybrid of steam and electric propulsion required significant manpower. During her final acceptance trials, 80 personnel were crowded aboard the submarine. This high complement included the highly trained naval crew required to run the complex ship, alongside numerous civilian engineering contractors brought aboard to monitor the experimental machinery during the deep dive. Everyone aboard understood the design's single point of failure. The boiler room inlets had to seat and lock before the boat could be safe below. The acceptance dive was about to test that dependency. As the submarine prepared for her test dive, the heavy machinery was set into motion. The sequence to seal the massive hull breaches commenced. The complex array of actuating cylinders engaged, intended to secure the 37-inch vents and restore the unbroken steel envelope required for survival below. 80 men waited within the tight confines of the hull. The acceptance dive was meant to prove the viability of this aggressive mechanical design. Instead, the inherent vulnerability of the immense hull penetrations was about to meet the raw power of the environment. Dropping a 10-ton keel weight was meant to drive a diving submarine back toward the surface. During the acceptance dive on January 29, 1917, the command team ordered the drop keels released. The forward 10-ton keel went, but the afterkeel could not be let go. With the stern flooding, the remaining weight aft and the incoming water overpowered the countermeasure, and the boat continued down. Moments before the dive, the order went out to shut and secure the boiler room ventilators. 4 heavy caps never fully seated, yet the sequence was treated as complete. Later divers would find the 4 inlets still standing open, with their control gear left in the open position. Inside the control room, the panel could confirm a command had been made. not that every cover had actually seated and dogged down. Whether by confusion, misreading, or an indication trusted too easily, the watch believed the inlets were secure, and on that belief, the officers took her down. As the heavy pressure boundary slipped below the surface, the ocean immediately exploited the 4 unsealed vents. Massive columns of freezing seawater poured directly down into the expansive boiler room spaces at the stern. The incoming water rushed through the gaps with immense force, violently displacing the internal atmosphere. The water ingress was absolute, rapid, and unstoppable. The stern of the vessel instantly gained catastrophic negative buoyancy. The aft compartments filled completely, dragging the tail of the heavy steel ship steeply downward. In the forward control room, the sudden angle of the deck communicated the massive loss of equilibrium. The commanders triggered the forward drop keel, trying to lever the bow upward against the flooded stern. But the sheer concentrated mass of the violently flooded aft compartments mathematically overpowered the massive buoyancy gain at the bow. The stern simply held too much ocean. The unarrested plunge continued until the hull settled into the mud of the seabed. Accounts placed the resting depth at about 50 to 55 feet. The descent stopped, but it left the forward compartments intact and the survivors trapped under the loch, with no reliable outside communication at first. 2 commanders locked themselves inside a narrow vertical steel tube and deliberately opened a valve to flood their own confined space with the freezing sea. Pinned to the seabed, the survivors faced a deadly delay before the surface could be certain what had happened and where the boat lay. The submarine could release a marker buoy, and once divers reached the hull, they could exchange simple signals by sound. But in those first critical hours, the men inside the intact forward section had no direct, dependable way to speak to the ships above, and the pressure on the hatches made any normal exit impossible. The tactical decision centered entirely on the specific structural geometry of the conning tower. This vertical access trunk featured a heavy internal hatch isolating it from the main control room, and a second heavy external hatch securing it against the ocean. The commanders repurposed this narrow intermediate space as an improvised differential pressure lock. A submarine hatch cannot simply be forced outward against the profound weight of an overlying water column. The pressure bearing down on the outer steel skin must be matched exactly by the pressure pushing up from within. To achieve that balance, the 2 commanders sealed themselves inside the narrow tower trunk, shut the lower hatch, and prepared to equalize pressure in a controlled way. They let seawater into the chamber while using high-pressure air to control the space until it was equalized, and only then did they unlatch the outer hatch. As the icy water forced its way into the confined steel cylinder, the internal atmosphere had nowhere to escape. The rising water level rapidly compressed the trapped air against the upper steel dome of the outer hatch. This created a massive, heavily pressurized bubble. The physical environment inside the flooding trunk became violently hostile. The severe compression of the air multiplied the internal atmospheric pressure, matching the crushing depth of the sea outside. This highly compressed gas pocket formed a tightly coiled kinetic spring at the top of the tower. They endured the compression until the pressures finally balanced, then threw the latches. Opening the hatch did not result in a gentle release. Releasing the heavy outer steel door instantly triggered a violently rapid thermodynamic reaction. The highly compressed pocket of trapped air was suddenly exposed to the open water column leading directly to the sky. It immediately and forcefully expanded, violently seeking the lower atmospheric pressure above. This rapidly expanding air blast essentially transformed the narrow steel trunk into an upward-firing pneumatic mechanism. The sudden massive displacement of the air bubble created a profound and uncontrollable kinetic surge. The water surrounding the hatch was violently shoved aside as the pressurized gas forced its way out of the confined steel tube. The sudden release expelled both men from the submarine. One was carried up through the water column and reached the surface alive, able to raise the alarm. The other did not survive. He was later found in the wheelhouse, and it is believed he was incapacitated during the escape attempt, likely after striking the structure above. This brutal operational gamble succeeded in punching a single human messenger through the heavy pressure boundary. A survivor now floated on the surface, ready to guide the rescue effort and confirm the existence of life below. But inside the dark steel cylinder on the seabed, the trapped crew was entirely cut off, rapidly exhausting their strictly finite volume of breathable atmosphere. Surface rescuers had no modern sonar to map the wreck in the dark loch water, so a diver had to work by touch along the casing to find the correct ventilator and rig a hose connection. Once secured, the surface ship drove compressed air down the line, freshening the forward spaces, forcing foul air out, and feeding pneumatic power to internal systems that could help manage buoyancy. The injected air was mechanically routed directly into the forward ballast tanks. By continuously forcing compressed gas into these flooded structural voids, the incoming high pressure physically displaced the heavy seawater, violently pushing it out through the open flood grates at the bottom of the steel tanks. As the dense ocean water evacuated, the extreme negative mass at the front of the submarine slowly converted back into aggressive positive buoyancy. The bow of the heavy steel cylinder became fundamentally lighter, shifting the mechanical equilibrium of the entire wreck. But restoring forward buoyancy was not enough to break the wreck free from the mud. To lift the survivors closer to daylight, the rescue force brought in 2 hopper barges and rigged heavy wire ropes beneath the forward hull. When the winches took the strain, the bow tore free of the suction and rose steeply, eventually lifting clear so that the forward section stood above the surface of the loch. The forward section of the submarine was now mechanically suspended near the surface, heavily secured by immense tensioned cables. The men inside were breathing clean air, injected continuously from the surface above. The massive dead weight of the flooded stern remained firmly anchored to the deep mud, turning the long hull into a steep metallic ramp. But the rescue operation was strictly stalled by the unyielding architecture of the ship. The massive steel pressure hull remained entirely intact, sealing the men rigidly inside the suspended steel tube. The surface rescue team faced a brutal structural dilemma. To pull the trapped crew from the heavy steel cylinder, they had to deliberately destroy the primary pressure boundary that was currently preventing the massive machine from flooding entirely. The heavy reinforced hatches designed for normal ingress and egress were entirely impassable. They were completely locked out by the severe geometric angle of the suspended hull and the immense hydrostatic weight of the surrounding ocean pressing firmly against them. The only viable mechanical path to reach the trapped personnel required cutting directly through the solid curved steel plates of the forward pressure hull. But initiating a massive thermal cut on a suspended, heavily loaded submarine introduced an extreme risk of immediate catastrophic failure. The massive steel tube was not resting securely on a solid foundation. It was suspended dynamically in an incredibly hostile environment. The heavy wire hawsers hauled aggressively upward on the lightened bow, while the massively flooded aft compartments dragged relentlessly downward, anchoring the heavy tail deep into the mud. This highly uneven support system fundamentally transformed the intact pressure hull into an immense, highly stressed mechanical beam. The steel skin was forced to manage incredible shear and bending forces. Slicing a large hole directly through the thick upper casing meant permanently severing the continuous steel fibers that handled this massive structural tension. The salvage engineers understood the brutal physics at play. Intentionally weakening the primary load-bearing envelope could easily cause the entire hull casing to buckle violently under the extreme uneven weight. If the steel cracked under the new stress concentration, or if the suddenly shifted mass caused the thick wire cables to slip, the mechanical equilibrium would completely collapse. The entire heavy vessel would immediately plunge backward into the depths, taking the trapped men and the freshly opened pressure hull directly to the bottom in an unstoppable catastrophic flood. Furthermore, the newly cut opening would sit dangerously close to the waterline, meaning any slight mechanical failure in the lifting system would instantly drown the men inside. Accepting this severe mechanical risk as the only remaining option, the surface team authorized a cut through the main pressure hull. After pumping out the space between the outer casing and the hull plating in the forward section, operators brought in oxyacetylene gear and burned a deliberate opening, about 18 inches square, through the curved steel. When the cut was complete, the night air rushed into the trapped compartment. The extraction sequence commenced immediately. Slowly and methodically, 48 men were individually pulled upward through the raw, hot edges of the shattered pressure boundary. They were hoisted entirely free from the mechanical trap and transferred securely onto the heavy floating salvage barges stationed alongside the wreck. Every living man originally trapped in the forward section was successfully pulled through the thermal cut. The massive operational gamble of destroying the primary structural envelope to achieve rapid human extraction had succeeded perfectly. but the heavy physical machine left behind was now fundamentally shattered. The immense compromised steel cylinder remained hanging precariously in the thick tension cables, aggressively unstable and highly vulnerable to the immense gravitational forces waiting in the dark water below. For roughly 55 to 57 hours, the trapped crew endured the extremes of the submerged wreck, fighting rising carbon dioxide and cold. The rapid physical extraction of the survivors from the shattered pressure boundary marked the formal conclusion of the immediate emergency phase. However, the sheer mechanical violence of the initial catastrophic plunge demanded a permanent human toll, as the deep flooded engineering compartments at the stern remained a sealed tomb. 32 men died in the disaster, most in the rapidly flooded after-machinery spaces when seawater poured through the open boiler room inlets, and at least one during the desperate escape attempt through the tower. The stark division between survival and death was still dictated by where each man was inside the machine as the stern compartments filled. The primary operational focus of the Surface Command immediately shifted from preserving fragile human life to managing a destabilized military asset. The weakened hull and uneven loads made the lift precarious. As water seeped in and the strain grew, fittings on the supporting barges were torn out and the submarine sank again to the bottom of the loch, now open to the sea and fully flooded. During a state of total global conflict, complex heavy machinery was an incredibly scarce and vital industrial resource. The highest levels of the Naval Command refused to abandon the submarine to the loch. A comprehensive secondary salvage campaign was organized to reclaim the hull. Instead of relying on external pontoons slung beneath the wreck, salvage teams worked compartment by compartment, sealing openings, fitting paired pipes for air supply and water discharge, and then using compressed air to drive water out. Over the course of weeks, and with pumps used to break the suction of the mud, the submarine was brought back to the surface as a badly damaged wreck, conclusively ending the salvage operation. The deeply compromised hull was secured and towed to dock for repair and reconstruction. The damage was made good, and the cut in the forward pressure hull was replated and reinforced, and the submarine was returned to service under a new designation, K-22. The underlying concept remained the same: a fast, surface-running, steam-driven submarine, carrying forward the same inherent operational risks that had already turned one acceptance dive into catastrophe.